All of physics, AP Physics, with mathematical logic and intuition. Of course, no calculus, I guess, but this should be all of Physics 1 and Physics 2. Alright, so this should be pretty simple. The AP exam is tomorrow, and I'm taking it, so this should be pretty simple. So first, we have to understand what a vector is. A vector is simple. A vector is something with direction and magnitude. That's all it is. It can be anything from theoretical, which means that it doesn't really exist, or in physics, it exists, and it's very, what is it? And we can use it for calculations. So there are two components to a vector, of course, magnitude and direction. Magnitude is essentially the shortest distance between 2 points, and it is how big something is, essentially, or how long the hypotenuse of the vector is. That's all it is. Direction is simply the angle it's pointing at. So let's say that a person walks this way, or walks 10 meters for 10 meters at a 45-degree angle. This means that they walk 10 meters here, and a vector would mean that that this bottom part can be written as 10 cosine 45 and 10 sine 45. So essentially, a vector is just is a mathematical representation of direction and magnitude. Now, magnitude without direction is called the scalar. And what a scalar is essentially something that is just a number. So like your weight is a scalar, pressure is a scalar, things like that is a scalar where it doesn't really have a direction. But if I say I walk north at like 10 miles per hour, that is, or if I walk north at 10 miles per hour, if I walk 10 meters north, all of those are vector positions and directions. And of course, this is just this simple logic. The reason is because these, if you plug them into the Pythagorean theorem, they'll give you 10. So 10 is simply the relation between, these are simply the relation of the components and its magnitude. And the reason why it's sine 45 is because sine 45 equals op over hype. And remember that the hypotenuse is just a magnitude here. So to get the opposite length, we get magnitude times sine 45, which is 10 sine 45, which is approximately, well, 45 is 45, so it'd be over square root 2 over 2. So approximately, do the math, I guess it would be 14.14, around 7.147. But of course, my math could be incorrect a little bit. But essentially, a vector is just something that relates position or magnitude and direction, and takes the relationships of a triangle, meaning that the other side. So like if I were to walk 10 meters, that would be the same as me walking right 10 cosine 45 and up 10 sine 45 meters, because the hypotenuse adds together to make a simple 10. That's literally all it is. Those are all vectors. Now, there are multiple things that are vectors. As I've mentioned before, center of mass is a vector. Momentum is a vector. Work energy theorem is actually not a vector, though it uses two vectors to calculate other things. Things like force, acceleration, velocity are all vectors. And that kind of gets us into the logic of distance versus displacement, which should be still chapter 1. I guess I'll just skim through chapter 1 and chapter 2 since they're pretty easy. How do I, okay, there we go. Wait, what? Okay. Okay, actually, maybe not that. Alright, we'll just do this. Okay, so distance is essentially a movement without direction. So if I move 5 meters here, let's say I'm standing here, I move 5 meters to the right and 5 meters to the left. Technically, I haven't moved at all because I'm back at the starting place. But distance says I've moved 10 meters. Displacement says I've moved none. So displacement is simply the vector between the initial and original position. So like before, a man walks 10 meters this way. That means the vector is 10 angle 45 degrees. That's all that is. And yeah, so you can add vectors by adding the complements, or essentially adding the x and y parts of the vector. Or in some rare cases, like if you're going in a straight line and you share the same angle, you can simply just add the vectors together by the magnitudes. So if I say I walk 10 meters east, and I walk 10 meters east again, there's no need for me to add the components because there's only one component, which is the x-axis component. That's all easy stuff, and we'll move on. All right, so let's go over velocity. Velocity, we'll go over the 3 relations. So position is the first relation, and position is essentially just where you are, of course, and that's a vector essentially, or not a vector, but that's just the first the first function, and velocity is the derivative of position. All that means is that velocity is how fast position changes over time. So I guess the accurate position is d position over time, or you can write this as displacement over time. And the way to calculate it is just like you think, just divide the displacement over the time. Although this isn't always the case, because there's something called instantaneous, which means the velocity at one point. Essentially what your speedometer says. But this is the change in velocity over time, so I put d velocity over dt. And this will be just velocity final minus velocity initial over t. And yeah, these are how to calculate each other. Although technically calculus isn't needed for this AP exam, they do expect you to know some calculus, such as the areas. So remember that the area under an acceleration curve is the change in velocity, and the area under a velocity curve is a change in position. And this is how you calculate it. So let's say you walk 5 meters in 2 seconds. That means your rate is 2.5 meters per second, which is your velocity. Speed is velocity, but instead of using displacement over time, it's distance over time, and we explained the difference between distance and displacement previously. All right, so just the kinematic equations now are all that are needed, which is chapter 2 and 3. So kinematic equations explains how velocity, acceleration, and position relate, just using 4 simple equations. All right, so the first one is VF equals VO plus AT. Second one is D equals VOT. And when I say VO or V naught, that just means the initial, plus AT squared over 2. And what it was, third one. Oh yeah, the third one I almost forgot, but yeah, okay. It's just the sum of velocity divided by 2 times t, or essentially the average velocity times time. And these are all derived. You can do it algebraically like I've done before, or you can take calculus and understand how this is formed, or you can just use simple logic and use, I guess, like a Riemann sum kind of deal. And the last one is the relation between the squared velocities. So Vf squared equals V naught squared plus 2ax. X is position, of course. Or maybe I should put d to be consistent because I use d here. So these are all the equations that are needed to calculate final velocity. Use these. Now these only work assuming constant acceleration. So if there are 2 accelerations given, you have to calculate them for 2 different times. So for example, if we're told that a car has a 5 meters per second squared acceleration for the first 10 seconds, and it starts at VO equals 0, and it has 10 meters per second squared for the last 10 to 20 seconds. Then we have to calculate a few things. So if it accelerates at 5 meters per second, that means it would have a final velocity of 50 meters per second, which means that the initial velocity from this interval should be 50 meters. And you can just plug them in, and you have to evaluate them separately, essentially, if the acceleration differs. Which should be pretty logical because there's only one place for acceleration to go anyways. Free falling bodies is the same thing. You just use the kinematic equations, but you are simply using them with replacing A with G. And G here would be negative 9.8. A negative displacement means you're falling downwards. A positive displacement means you're coming upwards. So it's literally the same thing for kinematics. Simply, like for the second kinematic equation, just do V naught t minus 9.8 over 2t squared. And yeah, you're just plugging in a constant for g. Whereas the kinematic equation can be used for any sort of acceleration, we're simply using gravity for free-falling bodies. That's literally it. Graphical analysis, velocity and acceleration. Just simple stuff. Velocity is the rate of change of a position. And you know how to calculate that simply using the slope formula, essentially, assuming that the velocity is constant. If it's not, then you'll have to use instantaneous acceleration or instantaneous velocity, which is just the velocity as the time goes to 0. Pretty simple stuff. Chapter 3.1 to 4 is essentially the same thing, except for 3.1 to 4, we are doing velocity in 2 directions. But remember that I said that that velocity and that velocity is a vector, so that means you can evaluate the x and y things separately. So before, as we were using v equals vo plus at, these are technically linear kinematics, which means like if it's 2D, I guess, one from here to here. But now you can have like here to here, like a ball or something. So like let's say that's 45 meters per second. Actually, maybe a little bit less. Let's make something a little bit easier, 10 meters per second. And I'll do 30 degrees because I know that's special right triangle. So that means you can apply these kinematics separately to see where it falls. So for example, this would be 10 cosine 35, or 10 cosine 30 to get the velocity. Cosine 30 is equal to square root 3 over 2. So that would be approximately, 17, so about 8.5 meters per second in the x direction. So this is the same thing as 10, 8.5. And here we could solve it using Pythagorean theorem, or 10 sine 30, which is just 1/2, so it should be around 5. Which looks pretty accurate based off the Pythagorean theorem. 5 squared is 25, 8.5 is around like 70. So 25 plus 70 is around 100, and the square root of 100 is 10. So that means you can, this is what's called Vy, this is what's called Vx, and you can tell how fast something goes separately. Or you can see the displacement in either direction just by breaking it into two. So for example, the displacement in the x direction can be calculated with the second kinematic equation, assuming no acceleration, of course. So that means at squared over 2 is equal to 0. So 8.5 times t, or how long it will be for, and that will tell you where it will land further down the line. That's all that means. That's all equations kinematics in 2 dimensions means. And of course, you can split them up into their respective things, but it's literally the same exact formulas, of course. So it's going to be Vf equals Vo plus, I guess, delta V or At. VOT plus At squared over 2. I hate writing this out. And what is it? Oh, yeah. Nobody really uses this formula, actually. This is kind of a useless formula, because you can simply just calculate the change in velocity and just use one of these formulas, so pretty useless. Last one is Vf squared equals Vo squared plus At. Sometimes you'll see it as or equal plus 2ax or 2ad to be consistent. And all that means is you can switch in the y direction, or the x direction. So x, 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 x. That's all that means. You can evaluate both of the things in different directions. Projectile motion is no different, except projectile motion uses gravity for the y direction. So instead of, like, let's take the second kinematic equation. Instead of at over square root 2, we have gt over square root 2, where g is a negative constant, negative 9.8. And using this, you can calculate the time it's in the air for. Assuming that you have the initial and velocity, or the initial and the final velocity, this is simply a quadratic equation. So be negative 9.81 over 2t squared plus Voigt minus displacement. And if you're given how high it is, then this will be minus height, actually. So this should be pretty simple as well. Plus Voigt minus height, or how high the ball is. Plug this into your calculator, use the quadratic formula, solve for t, and you can plug that t back into your x equations to see how far the ball has traveled in that direction. So that's pretty simple as well. Just using the kinematic equations once more. That's all of chapter 3. Essentially, other stuff is pretty easy as well. There's relative velocity, which is kind of useless too, as long as you can figure logic out. Imagine you're on top of a car that is going 5 meters per second. That means you're also going 5 meters per second. But let's say you're running on top of that car at 2 meters per second. So that means you're running at 2 meters per second, and this car is running. That's also very slow, I think. 2 meters per second. Actually, that might be fast. I don't know. 5 meters per second. That means you're traveling at 7 meters per second. So as long as you were logical, you could figure it out. But the formal formula goes as follows: VAB equals VAG. So the velocity of A relative to the ground plus VGB. And if you want to switch the subscripts, it would just be VAG equals negative VGA, and this goes for any subscripts pertaining to relative velocity. So VGB equals negative VBG. And the logic is as follows. Let's say that, so A relative to the ground means that imagine you're the ground and you see a car running this way. So this is you on the ground and a car is going this way. And that will be equal to the negative of the car relative to the ground relative to the car, because the ground appears to be going this way relative to the car, because you're in the car seeing the car or the ground go this way, so then it'll be negative of that. We could try a practice question, but I mean, it's pretty simple. Yeah, actually, maybe not. It's pretty simple. I just don't. There's no need to do so. Now, chapter 4 gets a little bit intuitive. You have to know Newton's 3 laws. First law is really simple. So first law is that something stays in motion, or I guess the more accurate version would be same speed if no force acts. And I guess speed is a little bit wrong. I guess velocity, if no force acts, is probably a little bit better. And the more formal stating of this that you'll hear is that an object stays in rest or in motion as long as no external force acts. Number 2 is that force is dependent on mass times acceleration, or force is dependent from mass and acceleration. And through that, the mathematical formula F equals ma is the third one. Or is the second formula, or second postulate. And the third one is that every action has an equal and opposite reaction. So if I push someone, they will be pushed back at the same force, I guess. So every force I apply to someone, a same force will be applied back to me. That's all that means. So this is called the action-reaction law. For every action, there's an equal and opposite reaction. All that means. Okay, next. Okay, so the concepts of force and mass. So force is a push or pull. Essentially, more accurately, force is the change in velocity per unit time amplified by unit mass. So it's essentially force equals m dv dt. And dv dt is ma if you're not taking calculus. That's pretty logical. And also the vector is more accurate. So yeah, that's all that means. So a force is something that causes an object's motion to change, or speed to change. So a ball at rest, if you apply force and it gets rolling, then that means you applied a force. An object's velocity will not change if a force is not applied. So only a force can make it change, essentially. And we've already covered all Newton's third law, so we can skip all this stuff. So F equals ma. So that means if I apply a 2 Newton force, and a Newton is equal to kg m over s squared. The logic is ma. M is units kg, and a is units m over s squared. So that's where this comes from. A Newton is the SI unit of force. SI unit just means using kg, meters, seconds, and stuff like that. So yeah, let's say you have a 2 Newton force, and something weighs 10 kgs. If you apply 2 Newton force, that means you are applying, remember F equals ma, and kg is the SI unit. That means you're applying a 0.2 meters per second squared acceleration. So that means every second, or for how long you're applying the force, you are applying an acceleration of 0.2 meters per second. And so if you're applying that force for 2 seconds, that means it'll be 0.2 times 2. Or if you want to get technical, 0.0 meters per second squared times 2 seconds. The s's cancel out to get 0.4 meters per second. And this will be your change in velocity. So again, remember, acceleration is just how much the velocity is changing per second. Though it might be a little bit more nuanced than that, but yeah, that's essentially what it means. Okay, the vector nature of Newton's second law. Remember, force is a vector. So if you have a 10 Newton force going this way, that can be the same as 10 and F45. You can break it apart into the y components and x components. All that means logical stuff. Newton's third law of motion already covered. Oh, so there might be a trick question, which is applying more force to one another. They're applying the same amount of forces. No one applies more force to another. 3 types of forces. This is probably not needed, but the 3 types of forces are gravitational, weak nuclear force, strong nuclear force, from what I remember, and electronuclear force. This kind of looks like electronegativity, but gravitational force is, as we all know, something that pulls something down to a center, or to its center of mass. Strong nuclear force is the force that holds the protons together in the nucleus. Electroweak force, oh actually yeah, it's electroweak, is a mix of the weak nuclear force and the electromagnetic force. So Coulomb's law and stuff like that. Weak nuclear force has to do with atomic, with the nucleus and atoms in general as well. The only one we deal with here is the gravitational force, which we'll get to right now. So what is the gravitational force? The gravitational force is calculated by this. M1, M2 divided by R squared. So it depends on two masses. So let's say we have like the Earth here, which is 5 kilograms, which is just definitely a heavy estimation. That's 4 kilograms. That means the gravitational force is G times 5 times 4 times the R squared. Let's say that they're separated by a distance of 1 meter, which is highly unrealistic, but obviously it's generalization. This is 20G divided by 1. And what is G? Well, G is just a constant, which stands for 6.674 times 10 to the negative 11. And if you want to calculate what that is, it's essentially just, well, let me do the logic real quick. What about kg times m squared? Sorry, kg squared. It will be m squared divided by kg. Yeah, m squared divided by kg times meters per second squared. Which will be m cubed over kg s squared, which will be the units. But this can be written as well, I guess this is it. But why did I put R2? This should be R squared. M squared. Yep. Yeah. So this is the units here, or you can rewrite it as Newton times m squared over kg squared. And again, Newton is m squared, or m over s squared, kg. So m squared over kg squared. Kg's cancel out top and bottom to get m cubed times kg s squared. So just like I said, though it took me some while to do it in my head, but maybe my mental math has gotten a little bit duller. So 20g over 1, g is the constant, this g times m squared over kg squared, which you don't really need to know. But to calculate it, it's essentially g m1, m2, r squared, as mentioned before. And so if we calculate the gravitational force between these two planets earlier, we'll get 20g times 1. You can plug that into your calculator. But that's essentially how much force one body is exerting on another. But likewise, Newton's third law says that it is applying the same force back. So gravitational forces are equal and opposite, much like Newton's third law, and much like every single force in existence. So that is how to calculate Newton's third law. With that, other things can be calculated, but right now that is irrelevant. What is weight? Weight is essentially just downwards force caused by gravity. So it's mg. Remember mg, or g, or I guess not mg. Well, yeah, mg is the formula. So depending on where you are on Earth, it changes. But if you want to plug g in because you want to find acceleration, let's go back to the original formula. The original formula is g equals g m1 m2 over r squared. I guess the more accurate would be fg, which is gravitational force. Why do I keep writing the subscript instead of the exponent? So that calculates the gravitational force. And now to get the acceleration, you just do g m1 m2 divided by r squared equals m1a. M1's cancel out because this is the gravitational force, set it equal to ma. So a is equal to g m2 over r squared, which is equal to mg m2 over r squared equals weight for any place. We say it here, but on Earth, since we know g is 9.81, you could just do the mass times 9.81. On the moon, it's 1.6, and so on and so forth. The normal force is quite simple as well. The normal force is how much force you exert on a surface. If you're just standing doing nothing, the only force being exerted on your body is the gravitational force, or weight. So weight is equal to mg once more. So yeah, this is just going to be equal to g m1 m2 over r squared, which is the normal force. But it gets a little bit different. So like, let's say you're standing here. Let's say you weigh 50 newtons. So that means the normal force, or the force you're exerting on the ground, is 50 newtons. But let's say I come along and push your head down, so you with the force of 5 newtons. That means the normal force is now 55 newtons because the newtons add up because of the vector nature of the newtons. That's all that means. So normal force is how much force you're exerting on the ground. Apparent weight is a little bit different, which is also kind of useless too. I don't really understand the theoretical applications. But think about this. Let's say you're standing, and let's say you're in an elevator. Remember that gravity states that everything falls at the same speed as long as both are at rest and there is no air resistance. But for physics 1, air resistance is never an issue. So that means everything falls at the same speed. Actually, that's a little bit inaccurate, but everything will hit the ground at the same time. Or same speed, actually. That can work too, because at every point it's the same speed. Though your mass, everything falls at the same speed. So let's say you're in an elevator and there's a scale down there. And let's say that the elevator falls down at the same time you fall down. That would mean that the scale would read 0, because it's actually not feeling your feet. There's no normal force. So apparent weight is essentially normal force. That's all it is. How much you weigh relative to your surface. So weight relative to what you're standing on. It's a platform, I guess. So like in a falling elevator where you and the elevator are falling at the same speed, your feet will never actually touch the ground, meaning that you will never actually exert a weight onto the scale. And the weight will say that you read 0 newtons, which obviously is not the case because you don't weigh 0 newtons. You weigh mass times gravity, which can never be 0 unless you are 0 mass. So then the logical idea is that the apparent weight, let me think of the formula. All right, let me derive it real quick. Ahead. Okay, well, mg, obviously. Oh, wait. How do I write that? I guess weights. Or actually, no. Oh, yeah, because the only thing that changes is m, because mass is constant. The only thing that changes is acceleration. This is the formula. Literally, I could figure out in my head. And the logic is that if the thing is going down at 2 meters per second squared, and gravity acts at 9.81 meters squared, or approximately 10 meters squared, that means you are technically only falling down at 8 meters per second squared relative to this. So again, it's like relative velocity, but now we're going into relative acceleration. So this means the only force you're applying is m times 8, or 8m in this case. So yeah, this is the formula there. Again, this is relative to a down. A down equals negative a up, which is the same thing as mg plus up, plus g a up. So that means if you're going up at 2 meters per second squared, that means the entire platform you are accelerating an entire platform at 10 meters per second squared. And remember, F equals, or actually it would be 12. F equals ma, so you'd be at 12m, which is your force. So apparent weight is just how much force you are exerting relative to the non-inertial reference frame, which just means a frame in which it's not really constantly moving. And that's all it means. So essentially your weight relative to a scale on the platform you're standing on. That's all that means. I just gave you the formula. Though technically it can be more accurately written, or that is probably the most accurate and compact definition. Or you could just do G plus or minus A, and you could figure that out, of course. What is frictional force? This is now 4.7. So we've already covered 4 chapters pretty simply. All right, so what is gravitational force? Frictional force. Frictional force is anything that opposes motion. Take a box on a platform. Technically, no frictional force acts right now. A frictional force only acts to oppose motion. So a frictional force cannot make something start moving. It can only make something stop moving or slow something down. As you know, if you're standing still, there's technically no frictional force acting upon you. There's Fk and F of s. So there are two types of frictional forces. The derivations for these are irrelevant because they were found experimentally. And they're equal to some constant times the normal force. Kinetic is a little bit less than static, and the logic is that means use of k will typically be less than a use of s, but it doesn't matter because the formula is constant for both. Same exact formula. So I guess you wouldn't need to know that. But the use of k will always be less than the use of s. And the reason is quite intuitive. Pushing an object in motion has less friction because it's already sliding past and stopping all of the... Well, the reason why friction occurs is because of little grooves in the material. And that way, pushing this box, when it's already moving, is already kind of like getting past that initial... It's kind of like activation energy in chemistry. You're already past the hump and it's easier to push. The same way it's kind of easier to... It's kind of easier to... I don't actually have an analogy. It's kind of easier to, I guess, like, run when you're already running, since you don't have to start up and get to that point. So these are the reasons. So force only acts parallel to the motion. So let's say I'm going this way. That means it will post me this way. Let's say I'm going at like 45-degree angle. That means it will return at a reverse 45-degree angle. These are the formulas to calculate it. So let's say your normal force, or how much force you're exerting, is so the difference between f of k and f of s is f of k is when you're moving, f of s is when you're standing still. So you need to overcome f of s in order to start moving, because you need to have a greater force than f of s for your body to start moving. And you need to have and once you pass that barrier, the friction force becomes less and turns into kinetic friction force, such that F minus F of k is equal to your net force. So here, like let's say this box weighs 10 newtons, and I use 10, and the normal force is also 10 newtons, let's assume. And let's say that the use of S is 0.1, which is probably pretty accurate, assuming this is like ice or something. Or maybe something even a little less slippery. Remember, the formula is use of S times the normal force, which is equal to 0.1 times 10 in this case, which means that only 1 Newton acts against you. So that means you need to overcome 1 Newton of force, and you need to push it with 1 Newton of force to get this box moving. And once you do, it'll immediately switch to kinetic force. So like, let's say use of k is 0.05. Remember, it's a little bit less. Oh gosh. All right. That means if you're pushing with 1 Newton of force and you overcome the static friction force, only 0.5 Newtons force will act against you. We apply this formula, which means that you will only be moving to the right with 0.5 Newtons of force. And friction is now just being subtracted from the force you were applying. That's literally all that is. And now we have to get to inclined planes, which should be quite easy as well. If you're on an inclined plane with a box, only works for boxes, by the way. Or actually, I guess anything that can apply a uniform force. The normal force is equal to mg cosine theta. And the force that is coming downhill due to gravity, or like the force, I guess force down the slope. I guess force slope I'll put is equal to mg sine theta. This is the logic. Take a ramp right here. I can do this pretty simply. Say this is theta. So that means normal force can only act parallel here. And remember, the normal force here is going to be a little bit less than the gravitational force. So that means the gravitational force will be the net vector. Gravitational force is mg. Normal force is this. But remember that the normal force is perpendicular to the surface. So straight down from any surface that you are applying. So this is the mathematical proof. This is theta. That means this is 90 degrees. This entire thing right here. So that means in this right triangle, this is also a right triangle, and this is 90 minus theta, which means that this has to be theta and this has to be 90 minus theta. Sine of theta here would be equal to, or mg sine of theta here, would be equal to this force. So whatever, so it looks like this. So mg sine of theta would be this downwards gravitational force, which is parallel to the slope. So mg sine of theta is f slope, and mg cosine theta is a normal force, which is how much force you are directly applying parallel to the surface, or perpendicular to the surface. Sorry, that was incorrect. 4.10 is just how much force you are applying with the, or tension force is how much force you are applying with the rope, typically with the massless string. And the reason why it's a massless string is quite intuitive. That means it doesn't interfere, and it's essentially just the force that is applied within like free body diagrams, and you don't have to worry about the rope at all, just the force it applies. 4.11, equilibrium applications of Newton's law. Remember that a force is something that causes an object's velocity to change. So this means if all the forces add up to 0, that means the object is not moving, or not. It doesn't mean it's not moving. It means that the object's velocity does not change. So if you're told in a problem that the velocity does not change, that means all the forces must add up to 0. And you could do some things with that. So like, let's say we have a ball. Let's say we have a box. Let's say there's a 5 Newton force this way. And it's not moving. Then how many newtons must be applied? This is quite simple. This means there's another Newton, or another force pressing this, so that they cancel out. And you can obviously do this with even stranger vectors, such as vectors with angles, or vectors with angles that are not 0 or 180. So like 45 degrees, and let's say this is a 6 Newton force. This means the summation, and we have a vector this way at 0 degrees. You either need the magnitude or angle in order to find the other one. So that means the forces must be equal to 6 cosine 45. We don't have to worry about y because it's a box that is resting flat. So we just need to know the magnitude of this. Has to equal the negative of cosine 0 force. Yeah, assuming the force is being applied this way, which should mean it's a negative 645, which is equal to plus f cosine theta. And you could solve for this pretty simply. Just divide cosine 0 on both sides. Remember, cosine 0 is just 1. Cosine 45 is square root 2 over 2. So this is negative 6 square root 2 over 2, which is equal to negative 12 square root 2. Oh, wait, no. What am I doing? Negative 3 square root 2 over 2 newtons of force. So the magnitude of this force vector would be equal to negative 3 square root 2. Pretty simple stuff as well. Just equilibrium applications. You do a lot of those, especially in torquing as well. Alright, centripetal acceleration. This one's quite difficult to understand. So what is the period of something, or not the period? What is the velocity of something traveling in a circle? It's 2 pi over t. It's 2 over t, how long it takes for one period, or a t period. Logic is quite intuitive. Take a circle. Let's say that it's 5 meters. That means 2 pi. That means the circumference is 2 pi, which is 10 pi meters. And you're traveling that in how many seconds it takes, which is the period. So it's essentially how long it takes for you to do a circle divided by, or how many meters in a circle divided by how long it takes you to travel that circle, which is just the velocity definition once more. Okay, now 5.2, centripetal acceleration. Centripetal acceleration, or centripetal force, or acceleration in this case, is just the acceleration needed in order to keep something of a certain velocity traveling in a circle. So like, let's say I'm running here at 10 meters per second. Let's say I can only run 10 meters per second at all. That means I will be running in a straight line forever. But a centripetal acceleration calculates how fast or how much acceleration you need in order to loop me around in a circle infinitely. So the formula is v squared over r. I have a proof on my on the other video if you're curious. That's 100 over r. R depends on how big you want the circle to be. So if you want it bigger, you can do it bigger or whatnot. Let's say that the r is 10 meters. That means I will have a 10 meters per second squared centripetal acceleration, which means that it takes me 10 meters per second squared in order to I need an acceleration of 10 meters per second squared, and it's always pointing tangential, or always pointing perpendicular to the velocity vector. and that would give me a perfect circle. So if I had a 10 meters per second constant acceleration, then I'll be traveling at 10 meters per second, and this will keep me infinitely readjusting my velocity vector 10 meters per second, 10 meters per second. Now, the centripetal force isn't anything new. It can be applied through tension. It could be applied to different things, like even pushing. If you push something inwards at 10 meters per second squared, then you will keep the object going in perfect circular motion. That's all that means. 5.3 is quite easy. So if AC is equal to V squared over R, how do you find the force? Well, you just multiply M on both sides, because remember that Newton says that MA equals force all the time. This is your centripetal force. So before that is the acceleration you need, and this is the force you will need. It's simply just acceleration times the mass, which means that you will need a force of this magnitude. And we don't say direction because centripetal acceleration always points inward, and there is no direction. It depends on where the position of the thing is right now. So if A is the magnitude, then you just multiply by M to get the centripetal force. Same logic as before. Banked curves. This one's quite easy, but I'm not going to do the derivation either. Your relationship to keep a car traveling on a banked curve, which is essentially a lifted triangle that's like wrapped around like a donut, like a car right here. In order to keep it this way, the angle of this must be equal to V squared over RG. So like, let's say you want a really fast car. What is it? If you have a really fast car, it will fly off. But if you have this equilibrium, then it will cancel out, assuming no friction, of course. The derivation is a ratio of normal forces, if you're curious, but I also did derivation on that earlier. And essentially, it is the angle you need such that gravity will keep this going in circular motion. The equation is this, and you can also make this like even more intuitive. Like, I don't know why they don't solve it. This will probably be the more accurate, or the more used one, or the more practical one. Satellites in circular orbits. So we learned in 4.7 that, so we learned in 5.3 about the centripetal force, and in 4.7 we learned about the gravitational force. In space, the gravitational force is actually equal to the centripetal force, because it's the only thing keeping the planets in orbit. And as a result, this is the same logic applied to satellites. The only thing keeping satellites in motion, or in circular motion, is the gravitational force. So if we plug in G, M1, M2, and we gotta put in M1 here. I'll put Earth, of course. M1V squared over R. Then V equals what is it? G M1 over ME times R on both sides, which will cancel that out. Over R, divide M1 on both sides. So V is going to be equal to the square root of G, mass of the Earth, divided by the radius, which is the derivation here. And that's how fast you need to go in order to not get sucked in and hit the floor of the Earth. This is the perfect velocity you need to go in order for you to go in circular motion. Pretty simple stuff. 5.6, apparent weightlessness. Same thing as apparent weight before. F equals mg plus a. Plus or minus a. This one's pretty useless. I actually don't understand this one. I actually don't understand why this is needed. But yeah. Also, if you're given the velocity, this is tangential velocity, or how fast you are traveling in a circle, but with meters per second. So just regular velocity. Remember that the formula to calculate the entire circumference is 2 pi r. So 2 pi over r over v is equal to 2 pi r divided by square root gme over r. There's probably a bunch of ways to solve this, but essentially 2 pi r over v is the period. So the time it takes for something of a satellite to travel around infinitely is going to be equal to 2 pi r times square root r over gme, which is approximately equal to 2 pi, or not approximately, exactly equal to 1.5 over square root gme. And square root gme is just depending on, not exactly Earth either, it could be any orbiting planet, just anything that relies on a gravitational pull as a centripetal force. So this is the formula to calculate the period of something traveling in a circle. And a period is just the time it takes to do one full revolution. Vertical motion. So let's take a ramp, and let's say that you are not a ramp. I guess like a hamster wheel. And let's say that you are a bicyclist, or actually, yeah, a bicyclist, and you want to travel this way. There are 4 points where we can accurately determine the centripetal force. Any other points would require probably calculus or a little bit more intuitive thinking. So here, no centripetal force is needed. Or what is it? Yeah, 1 second. Okay, so the ramp here is what is providing the normal or providing the centripetal force. So like imagine swinging like a plane in a circle. You are the one providing the centripetal force by holding that string that is keeping that airplane in like a circular motion. In this case, the ramp is doing so. So that means the ramp is providing the normal force. So the force at the bottom is quite intuitive. Normal force, again, is the weight you are weighing plus whatever additional forces are added. In this case, the ramp has to provide another centripetal force. So this is the formula here. If it didn't apply the centripetal force, the bicyclist would just fall off the ramp. Number 3, it's simply just equal to the centripetal force. There's no gravity because gravity only acts downwards. So that means the only thing needed is the force needed to keep this in a circular motion, which is mv squared over r. This also applies for 3 and 1. For 2, it's this, and for 4, it's going to be Fn equals wait, mv squared. Wait. Okay, I gotta use some logic here. Okay, it's gonna be mv squared over r minus mg. Is this right? Let me check my book. Wait, number 3. Oh, it's number 3 in this one. And yes, this is right. The reason being is that if the centripetal force is higher, for example, let's say, then this means that this would have to provide the centripetal force, but mass times gravity is going to alleviate some of the centripetal force because there's already a force acting down. So the force needed is not going to be as heavy because the centripetal force will be aided by the gravitational force. That's the logic here. Just memorize those 4 formulas. Should be quite easy to do. If not, you can make them up on the test if you know at least a little bit of algebra and logic. Work energy theorem. This one is quite hard actually. So I guess you would have to do so. So work is equal to force over distance, but only force applied in the same direction as distance. So if you have a vector like this, and let's say you have a force here, which is 10 and 30, then here, which is 10 cosine 30, that would approximately be 10 square root 3 over 2. This would essentially imply that if you have a displacement of like a box that goes this way, and it goes 5 meters, then you can only use this to calculate the force. So the actual more better formula is force times distance cosine theta, which in this case would be 10 times 5 times the cosine of 30. But this is not universal. Again, you have to calculate the overlap between the force. In math, it's called the projection of v onto u. But here, it's essentially just the overlap between the two vectors, the position and the force vector. So, for example, let's say that you are traveling here 2 meters per second, or you travel 2 meters to the right, and you have a force of 20 meters. Since they're going in the same direction, then you can calculate it that way. You cannot calculate it if it's like 20 newtons here and 2 meters this way. You would have to find the overlap or the x of both. And also you would, and for y, you also do the same thing. Let's say that a piece is moved 2 meters and 5 meters this way. So 2 meters to the right, 5 meters up, and you have a 20 Newton force at like 30 degrees. Then you would have to break this into its components, which is 20 cosine 30, 20 sine 30, and you do the individual ones together. So that would be 40 cosine 30 plus 100 sine 30 is the amount of work you do. That is work. But why is work important? Well, work is equal to the change in kinetic energy, which is what you learn in 6.2. The derivation is not very clear. In this book, they use the second kinematic or the fourth kinematic equation, but that's kind of like incorrect in a sense because the fourth kinematic equation, I think it was proved using some calculus logic. But work is equal to the change in kinetic energy, and kinetic energy is equal to mv squared over 2 minus mvo squared over 2. So that means whatever work you do will change the kinetic energy. Note that kinetic energy squares the velocities, and for people who don't take calculus or linear algebra or anything revolving vectors, it doesn't matter the direction of the velocity here. The work to kinetic energy formula will simply tell you the change in kinetic energy and will not tell you the velocity. So like let's say you try to solve for VF. Equals work plus mvo squared over 2. Since you're just adding this to the other side, times 2 divided by m, and then square root all of it. The only issue is that, again, remember this only this direction doesn't matter here, so the velocity that you solve for will not give you the direction, it will just give you the velocity. So I think the more accurate version would be W equals ms squared, which is for speed, minus ms0 squared over 2. But again, like I guess it doesn't really matter here. All right. So gravitational force is equal to mgho minus F. Logic is, remember, work equals force times distance. The force here is gravitational. And the displacement is how much it is falling down, so it's HO minus HF. Not HF minus HO, because HF minus HO, if HF is higher, that means that the initial position is higher, and the work cannot be positive if it was HF minus HO. If we did have HF minus HO, it would be positive work and a positive gravitational force, which would imply that you did a positive work when the displacement and force act in opposite directions. That's pretty simple. Potential energy is equal to mgh, which is essentially how much, this calculation tells you how many joules can be converted into kinetic energy. The SI unit for work is kinetic energy, or is joules, and this will tell you how much work can be converted. So the formula relation is P, potential energy equals negative times the work. Conservation of mechanical energy, I won't do the derivation, but essentially it states the formula for non-conservative energy is EF minus EO, and EO is simply the sum of all energies that you'll learn. In physics 1, you will go up to rotational energy. So EF is essentially the sum of mgh plus mv squared over 2. So this will be the final version, so FF minus mgho plus mv0 squared over 2. You will go to rotational energy, so typically there will be an IW squared term added, but in this case it wouldn't really matter because we're talking about the work energy theorem in particular. Okay, now power. Power is simply the change in work over time, so much like velocity is change in displacement over time. Power is equal to how many joules you commit, or the change in power over time, or the change in work over time, or change in energy, I guess would be a little bit more thing. And understand that the integral of work is simply going to be equal to the change in kinetic energy. All right, impulse and momentum. This should be quite easy. I guess I'll skim through this. Impulse is defined as Ft, or F delta T, which is force per unit, or force over time. So let's say that you apply 2 Newton force for 5 seconds. That will be equal to 10 impulse, or 10 Newton seconds, which is the measurement for impulse. And 10 Newton seconds is the impulse. But what is impulse equal to? Impulse is equal to mvf minus O. The logic is quite clear. F is equal to ma delta t. A delta t is equal to change in velocity, so it's m delta v, which is the exact same thing here. So that means in this case, 10 Newton seconds would be equal to the change in linear momenta, which we'll get to it in a little bit too. So the principle of conservation of linear momenta, I won't do the proof, but the logic is quite simple too. 1 second. Yeah, I guess this is quite. I won't do the proof then, actually. It's quite rigorous. Or not rigorous, but it involves using Newton's third law, which I've already done before, so I guess it doesn't really matter. So, all this means is that the sum of mass times velocity must equal a constant. So, I'm going to use the summation. So, like, let's say we have, assuming that there are no external forces, which is what we'll do in conservation of linear momenta. P is equal to V, which means that PO must equal PF. And I'm going to use the summation notation here. So this means like if there's a 2 kilogram billiard ball or something, which is probably very, very inaccurate. Billiard ball is not 5 pounds, but in this case we'll do so. And it's traveling at 10 meters per second. That means 2 times 10. And let's say one-dimensional because momenta is also a vector. And let's say there's another billiard ball coming in at 5 meters per second at 4 kgs. And this has to be minus actually because it's going in a negative direction. Minus 4 times 5 is equal to 0. So that means this can never change. The sum of momenta will always equal 0 no matter how you distribute it. So like let's say that after the collision, this is traveling at like well, the mass is constant because mass is not going to change after collision. 2 times like 3, so 2 times 3 plus like so that's 6, so we have to have a negative 6, so that'd be negative 4 times 1.5. So that means this would have to travel at negative 1.5 after the collision if this is traveling forwards at 3 meters per second. That's all linear momenta is, essentially that the sum of mass times velocity are constant. Collisions in 2 dimensions, the same thing. You could just split up the x and y velocities and then just do it together as well. Pretty logical stuff. And now we get to something a little bit more intuitive, or a little more difficult. Center of mass. Center of mass essentially is the sum of average positions. The logic is that we can use this for torque, which we'll get to a little bit later. But this should be quite simple as well. M1x1 plus M2x2 is going to be essentially equal to 1 second. Center of mass. Okay, so remember, so M1x1 plus M2x2 is going to be equal to M2x2 plus M1x1, which essentially states that, let's say that the masses combined together, or not, react as the masses combined together, will be equal to M1 plus M2, I guess, plus X center of mass. So if we divide the center of mass on both sides, or divide M1 plus M2 on both sides, we get M1x1 plus M2x2 divided by M1 plus M2, which is more accurately XCM equals MIXI over M of I, which is the formula here. So essentially the product of the mass and the position relative to a starting point divided by the mass, which will give you the center of mass. Now the reason this is needed, I'm not too sure actually, but it is needed for some reason. Of course, I actually don't know why. You never really use this either. I guess we'll use it for torque, but I mean, yeah, I mean, I just really don't know why we learned this in physics, but this is the center of mass. I mean, I guess we'll use it for torque, which is also pretty intuitive. But remember that XCM is going to be a position function, essentially. So if the XCM changes, so delta XCM is equal to XCM final minus XCM initial. And if you divide this by time, you get the velocity of the center of mass. So the velocity of the center of mass is equal to mx or mixi which is just a sum of the products of mass times position. Of course, you can use any units, but in physics, we'll be using meters and kilograms, and then divided by time will give you the center of mass. Yeah, so that's all that means. Of course, you have to break it up into its initial vector positions. So that's all center of mass, and now we get to torque, which is a little bit more difficult. We will skip all rotational kinematics because it's the same exact thing. Because kinematics relates to the first and second derivative of anything. Then rotational kinematics, where W is equal to rads per second, alpha equals rads per second squared, and theta equals rads. Then you can just apply the same formulas as the first one, which is going to be WF equals WO plus AT, or alpha T, and so on and so forth, where W is the equivalent of V, or omega is the equivalent of V, alpha is the equivalent of acceleration, and theta is the equivalent of displacement. That's all that is. But now we get to dynamics for rotation. No? Motion? Which is essentially a lot easier. So there's something called curvilinear motion, and there's rectilinear motion. Pure translation is called rectilinear motion, and pure translation just means like no spinning, essentially. That's all that means. But like let's say we have a door, and we want to open the door. Okay, so let's draw from the top of the door. I'm not the best artist, but this should be quite simple. This is a door. This is the hinge. Well, someone figured out, and I'm actually not too sure which scientist, but someone figured out. Well, I guess anybody can figure out. Let's say that you push at the base. So like try to open a door from like the very end. It's gonna be really hard to do. So someone figured out torque is equal to force times radius. Well, technically with the cosine theta, but this is just to ensure that that they are pointing in the same direction. And r is not actually radius, though you can treat it as radius because it's simply the where you are applying the force. So if I'm applying the force from right here, this will be r. This midway point will be r. So that means the torque will be equal to, like, let's say that's 2 meters, and the force I'm applying is like 3 newtons. That would be 6 newton meters. Technically meter newton, same thing. This is not to be confused with work, which is newton meters as well, because that is joules, but here we are talking about torque. So we figured out that the more effective pushes happen at the end, which matches this formula, because the torque is higher, because the product of a higher number will be a higher number. So that is the logic there. But you have to ensure that the force and the radius, and the lever arm are perfectly perpendicular. So if we have, let's draw that again. And let's say that, okay, I'm such a bad artist. Let's say, actually, let me just use this picture, because, okay, so we have a door. This is the doorknob. And let's say that we push the force at a 45-degree angle. This means the force vector looks like this, 45. But remember, the force vector can actually be broken up into its successive vectors. So this 45-degree vector is the same as, like, let's say it's a 3 Newton force, 3 cosine 45, and 3 sine 45. And they have to be perpendicular, so it would be 3 sine 45, which is technically the same as cosine 45. 3 sine 45 is the force in the effective y direction times the lever arm, which in this case we will say is 3 newtons, so it would be 9 sine 45, which is the torque. Now, what does torque actually tell you? This is where we get into a more systematic approach to torque. So torque technically is equal to the second law of Newton's second law, but except we have a different notation here. We have torque is equal to I times alpha. Alpha, remember, is the equivalent of A, but in rads per second squared instead of meters per second squared. Remember, torque is Fr, so Fr equals Ia, and the proof starts like this. Let me see the proof, actually. I remember it was quite easy as well, but if I can't find it, I guess I'll have to prove it myself, which should be pretty easy as well. Okay. So also I is equal to mr squared for point masses, but for certain geometrical shapes like spheres, for example, it's 2/5 mr squared. And there's a bunch of different charts. So you won't have to memorize any of these. You might have to memorize the sphere or the hollow disk, which is mr squared, and the solid disk, which is 1/2 mr squared. But it wouldn't really matter for there. They use the calculus for that. You don't really have to understand why. So here's the proof as follows. Remember that torque is equal to ma. So force R is equal to MAR. But remember that A is equal to R times alpha. This is just math. Rads times the radius will give you the meters of that arc. And then to solve for AT with RA, we just plug this back in. So BM RAR, which is equal to mr squared times alpha, and that is where the formula comes from. So that means you can calculate the second derivative of angular position just using this relationship. That's all that means. We'll move on. And with that, you can use the rotational kinematics that we explained earlier with those formulas such as WF equals WO plus alpha T. The second one is WF, or not WF, theta, which is essentially the equivalent of meters, and or displacement is equal to that. So before we define rotational energy, or we define mechanical energy as the sum of the gravitational potential energy and the kinetic energy. But now we have to introduce another term, which is going to be the rotational energy, which is just going to be IW squared over 2. The proof, I'm not aware of that, but this is just the formula now. Remember that mechanical energy is conserved, so this at one point has to equal this at another point, which should be quite easy. And you can also apply the work energy theorem here, where work is equal to the change in kinetic energy. But now it's going to be equal to mv squared over 2 plus iw squared over 2. This is just potential, so it doesn't matter. And that will be equal to mvf squared minus vo squared over... oh, wait. No, hold on. From the proof, I remember it's 1 plus k mr squared over 2. Or mv squared over 2. The radiuses cancel out, so that will be equal to work, and this is the formula that will be needed for most of the things. K is the constant behind the mr squared. So if you're doing a sphere, it would be 2/5. If you're doing a filled-in rod, it would just be 1. So K, this is the formula to calculate the tangential velocity from how much work you are doing for an object that is rolling down a ramp, or any rolling down a ramp without slipping. That's the formula here. And the reason why this is kind of difficult to understand is because they don't explain it at all. You're just expected to know that. One more thing is that rotational momenta is conserved, so the summation of IW initial must equal the summation of IW final, which is quite intuitive and logical as well. Alright. Again, I guess there's only like a few things left. The ideal spring, force equals kx. So this is Hooke's law, I guess. Well, actually, Hooke made the restoring law as well. But essentially, this is a spring constant with the formula Newton over meters. And essentially, this gives you the relationship between how much force you apply, and this is springs, to how much it gets displaced. So like, let's say you apply 2 Newton force, and the spring constant is 0.5. That means that x has to be equal 4. So that means a spring will compress 4 meters if you apply 2 Newton force to it. A restoring force is the same logic, except that in this case the force will be opposite. So the negative is just to indicate that it will be opposite. So when you let go, it will apply a negative 4 meters back and forth. The other stuff is just relationships between sinusoidal functions and waves. So for the position function, let's take a object moving around in a circle. This will be equal to a cosine wt, or a cosine theta. Remember theta is wt, so it's going to be a cosine wt, relating the omega to an object moving in circular motion. We're only taking the x direction to get a periodic motion, to get essentially a simulation of a periodic motion. A is the hypotenuse, so this calculates the x position at any point in the circle. So a cosine wt. This is going to be equal to x of t. So v of t would again be the derivative, which is going to be equal to negative a w sine wt using chain rule, and a of t is equal to negative a w squared cosine wt for acceleration. You can do this algebraically, but I'd rather not. And this means that the acceleration max is equal to aw squared, because cosine wt's max is 1. So that means the greatest acceleration you could have is aw, which is going to be at the center, because at the center, that's when cosine wt is equal to 1. That's all. And energy is pretty simple too. Remember, work is equal to force times distance. The force here is Hooke's law. This will calculate the force at any point. And D is going to be equal to XO minus XF. But remember that, what is it? Remember that the force changes over time. And the force changing over time will be a little bit of a nuisance to us. So what we're going to do is we're going to use the average force. And the average force, though technically you can use this if you have a function and you can integrate it properly. This is the formula for if you do not want to use calculus and you just want to derive it. I know it seems a little bit intuitive because before it was mvf squared over 2, but now it's kxo squared over 2. The logic is that the average force is just going to be kx 0 plus kxf over 2 times xo minus xf, and doing the algebra you get kx0 squared over 2 minus kxf squared over 2. So that will essentially be the work energy theorem that we have to deal with, and that will be equal to how much energy it is and how much work it can do on an object. So this is how much work it can do on an object depending on the initial and final positions. The last things you need to know for this chapter are just how to calculate the omega based off a spring. I already did derivations before. It's w equals k over square root m. And for period, you just multiply by 2 pi and swap the 2. The reason is because you have to do 2 pi over w, which will give you the period, and you do it on both sides. And for a pendulum, which is an object that swings back and forth, w equals square root g over l, and t equals 2 pi, and then you just swap the 2 like normal. Yeah, damped harmonic motion again is irrelevant. But I think Young's modulus is important too. Okay, Young's modulus is essentially a spring, or stress strain in Hooke's law. Young's modulus is the idea that, like before with the spring, if you press a spring in 2 meters, it will oscillate between plus or minus 2 meters from the initial starting point. So it's going to be like -2, and then it'll go right here, and then it'll go all the way to +2, and it will oscillate between this interval, where this is 0 and this is +2, -2. It will oscillate between these two back and forth, because nothing is taking that energy away from the spring. So stress strain in Hooke's law is much similar, except now it is relating the force to how much an object will be pushed in. So before, like a spring, F equals kx, depending on the constant, you will have a certain amount pushed in. But now we have multiple formulas. We have the shear bulk and Young's modulus. Young's modulus is for just any object that you are just applying a force to at the end. It's going to be equal to y, which is just the constant, much like the spring constant, times delta L over L, which should be unitless because it's the ratio of the two, times the area. Again, this isn't really needed to know. This is just or it's not actually given on the formula card, but this is the formula. For bulk modulus, okay, so this is for regular things, but for shear modulus is force not really applied to. Shear modulus is for things that can deform without stretching or compressing it, or without pushing and pulling in. So this can be like using your hand to apply a force to the top of a book, and the book, instead of being pushed to the right or whatever, will look something like this. The formula is going to be equal to S times delta X, that's not an integral sign, over the original position times A, or they use L, but same thing. Delta X is the change in the top of the book. Or not, well, like this would be delta X right here. And LO would simply just be the height of the book, and area would be the top of the book. How they figured this out, I'm actually not sure at all. Probably a bunch of curve fitting, but that's essentially it. And the bulk modulus is that the difference in pressure is equal to negative B delta V over VO times the cross-sectional volume. Wait, no. Times no volume at all. The volume is already factored into these top equations. There we go. That's essentially all of chapter 10, and now there's just chapter 11 left, which should be quite simple as well. This is simple too. Okay, so I guess I'll just do this really quickly. So density is the definition of how much mass is per unit volume. And we're going to be dealing with fluids that have constant density or are otherwise what are considered incompressible. We have P equals F over A, which is pressure equals the force times area, or force divided by area. And that will be in the units pascals. You will be using newtons divided by meters squared, which is equal to Pascal. So that additionally, pressure is not a vector because it points in all directions, so it's a scalar. And you can also get into a lot of calculus with that, with things like vector fields and whatnot. The pressure in a static is a pressure in a fluid is just P equals PO plus PGH. So where PO is the atmospheric pressure right above the point that you are measuring. So like let's say this is water. If you want to calculate the pressure down here at like down 4 meters, the formula will be P0, which is atmospheric pressure, which is 101.325 kilopascals or 101.325 pascals, plus water, which is 1,000, gravity 10, the height 4. That will calculate how much height. That's approximately equal to 40,000. So this will be equal to 141.325 pascals if you were to calculate the pressure at the bottom of this fluid. Equation of pressure gauges are pretty simple too. It's just barometers and manometers. Pascal's principle is easy. They try to complicate it, but essentially it just states that P2 equals P1, assuming they're at the same height. So any pressure change that you apply to one side must be applied to the other side as long as they're at the same height. Or actually, Pascal's principle more specifically is that a pressure change will be felt by everything within the container. But this is the more general formula. And again, remember, pressure is defined as force over area. So they can generalize the formula to F2 equals F1 A2 over A1, which in this case, you can use this to calculate the force at the other side of like a machine. So like remember, it only works for two things at the same height. So if you want to calculate the force upwards here and the force downwards here, then you will use this formula relationship that the force here is equal to the force here times the area divided by the area. That's all that is. Now we get to Archimedes' principle, which is quite easy as well. Archimedes' principle states that the force that will be pushing upwards on an object in water will be equal to the density of the object times the volume times gravity, or the density of the fluid, I mean. Remember, P times V is just equal to mass. So this would be mass of the fluid. I almost put water, but it works for water, works for oil, works for any fluid. And it's equal to this. The logic is also quite intuitive, but this is all you have to know. What is it? So the force, or this is called the buoyancy force, is equal to how much the weight of the water you displace. And with some logic, you can figure out that the P of the object divided the P of the fluid will tell you how much of the object is in the water or out of the water, or is equal to the percent of object in the fluid. So that means, let's say that the density of an object is 900 and the water is 1000, as we know. That means 0.9 or 90% of the object will be above the water. Yeah, I guess I should put ratio. So 90% of the object will be submerged. Object submerged in fluid. And this makes sense because if it is heavier or if it is more dense than the water, it will sink to the bottom, which we all knew from 7th grade science. Fluids in motion talks about mass flow rate. The mass flow rate is essentially how much water comes out, recorded in mass, divided by time, is equal to the density times the area times the volume. So that means that for something with an even mass flow rate, which is essentially anything with an even mass flow rate will be equal to each other. So that means the delta M over delta E must be constant. So the delta M at point 2 must be equal to delta M1 at point 1, which is just going to be equal to P1 A1 V1 equals P2 A2 V2. But we notice that P1 and P2 will be the same because we are in the same fluid. So A1 times the velocity will equal to A2 times the velocity. And the area can change, of course. So if it goes from a bigger pipe to a smaller pipe, the science tells us that here the larger area will have a lower velocity and the smaller area will have a greater velocity. Bernoulli's equation requires a proof using pressure differences times the volume, but the logic is much like the conservation of mechanical energy. The formula is P plus PGH plus PV squared over 2 is a constant, which means that P1 plus PGH1 plus PV1 squared over 2 must equal P2 plus PGH2 plus PV squared 2 over 2. That's how you can use this. So yeah, that's essentially all of AP Physics, pretty simply.